Hey everyone, welcome to The Explainer. Today, we're going to talk about something you probably never even think about, but it's in everything electronic you own. We're talking about the humble resistor. So, here's the game plan. We'll start with what a resistor even is and how it manages to control electricity. Then, we'll check out all the different types, crack their secret color code, and finally, see how they work together out in the real world. All right, let's kick things off with a little question for you. What do your phone, your TV, and your computer all have in common? And yeah, besides the fact that we can't seem to live without them. Well, the thing is, all of them, every single one, completely depends on this tiny, little, unsung hero of the electronics world to even function. Okay, so let's pull back the curtain. We are talking about resistors. They're these tiny components that are, and I mean this literally, what make modern electronics possible. So what in the world is a resistor? Well, think of it as a speed bump for electricity. Its entire job is to get in the way and slow down the flow of electric current in a circuit. And its job is just absolutely crucial. By slowing things down, it can control exactly how much power gets to other parts. It can split up voltages, fine-tune electrical signals, and maybe most importantly, it acts like a bodyguard for really sensitive components, protecting them from getting fried. It basically brings order to the chaos of electricity. Right, so how does this little thing actually manage to control something as powerful as electricity? Let's dive into that. Okay, probably the best way to get your head around this is with an analogy. Picture water flowing through a big, wide pipe. Now, imagine a section of that pipe suddenly gets really, really narrow. The water can still get through, but not as much and not as fast. The narrow part is the resistor, and the water is the electric current. So that squeezing of the pipe, that opposition, that's what we call resistance. It's something we can actually measure, and the unit we use is called the ohm. The more ohms a resistor has, the tighter the squeeze, and the more it restricts that electrical flow. And this whole relationship is wrapped up perfectly in something called Ohm's law. It's a beautifully simple formula. Voltage equals current times resistance. For an engineer, this little equation is a superpower. It lets them calculate the perfect resistor to get the exact amount of current they need right where it needs to go. Of course, one size doesn't fit all, right? Different jobs need different tools, and it's the same with resistors. There's a whole variety of them out there, each one designed for a specific task. I mean, even if we're just talking about your standard fixed resistors, the ones that have one set value, there's a bunch of options. You've got your basic carbon resistors. They're the workhorses, super cheap and great for everyday stuff. Then there are metal film resistors for high precision jobs where you need things to be super stable. And then you have the big guys, wire wound resistors. They're built to handle a ton of power without even breaking a sweat. But things get even cooler when we talk about resistors that can change. You know the volume knob on a stereo? That's a variable resistor called a potentiometer. A light dimmer switch? That's another one, called a rheostat. There are even specialized resistors that change based on their environment, like thermistors that react to heat or LDRs that react to light. So, with all these thousands of different resistor values, how on earth do you tell them apart? They're tiny! Well, that brings us to a super practical, kind of fun part, learning to read their secret language, the color code. I know, it might look a little confusing with all those stripes, but it's actually a pretty clever system. First thing you do is find the gold or silver band and put that on the right. Then you just read from left to right. The first stripe is your first number. The second stripe is your second number. The third stripe tells you how many zeros to tack on at the end. That last band, the one on the right, is also really important, but we'll come back to that in a minute. Now, trying to remember that color order from 0 to 9, yeah, that can be tricky. So, engineers came up with some, let's just say, memorable phrases to help. A really common one is, bad beer rots our young guts, but vodka goes well. The first letter of each word gives you the color. Black, brown, red, orange, and so on. Hey, whatever works. All right, we've got the theory down, we know what they are, we can even read their secret code. So now, let's see how they actually behave out in the wild, inside a real circuit. See, resistors almost never work alone, they're team players. You usually connect them in two main ways. If you link them up end to end, that's called series. And when you do that, their resistance just adds up, creating one big speed bump. But if you connect them side by side, which we call parallel, it's like opening up more lanes on a highway. You're giving the electricity more paths to take, so the total resistance actually goes down. Okay, now let's go back to that color code. Imagine we read the bands and figure out our resistor is supposed to be 1,000 ohms. We call that its nominal value. It's what the resistor is supposed to be, but the real world isn't always so perfect. And this is where that last band, that gold or silver one, comes into play. It's called tolerance. A gold band, for example, means the resistor is accurate to within 5%. So for our 1,000 ohm resistor, its actual resistance could be anywhere from 950 to 1,050 ohms. Now, for your toaster, who cares? But if you're building a sensitive piece of medical equipment, that little 5% difference is a very, very big deal. And, like anything, they don't last forever. They can fail in a few different ways. Sometimes they just break, creating an open circuit that's like a washed-out bridge. Nothing gets through. Or they can fail and become a short circuit, offering no resistance at all, which can be dangerous. And sometimes over years of use and heat, their value just slowly drifts, changing over time and messing with how a device works. So yeah, there you have it. This tiny little component with its colorful stripes is a genuine hero of the modern world. It kind of makes you stop and think, right? What's another one of these invisible innovations that we all completely depend on and just take for granted every single day? Something to chew on. Thanks for tuning in.